Welcome to quantum computing, where the boundaries of classical computing are pushed to the limit. I am your host Roshan here, and I am excited to take you on a journey into the fascinating world of quantum computing. In this channel, we will explore the latest developments in quantum computing, from quantum algorithms, quantum information theory, to the quantum machine learning. So, if you are ready to unlock the secrets of the quantum world, subscribe to my channel and join the quantum revolution. So, yeah, before getting into the quantum computing, it is necessary to have a few basic understanding of quantum concepts. There will be Moore's law, quantum tunneling. We'll see in the next slide. Okay. So, first thing, difference between classical computers versus quantum computers. We all know that classical computer uses bits representation, that is none other than binary representation for computation. Whereas in quantum computers, it uses qubits that can mean superposition. Remember that these two terms, qubits and superposition, will be using the terms throughout the course. And then quantum system process multiple states simultaneously. That means in a quantum system, let's say there will be 2 states, 4 states, 6 states, whatever it may be. The computation across all these states can happen simultaneously together. And quantum parallelism enables solving certain problems faster. This means, suppose let's say a classical computer takes 10 days or 20 days to solve a complex problem. The same problem with quantum computer, it takes 5 seconds to solve it. It have been proved by Google recently. Okay, Moore's law. It was given by Gordon Moore in 1965. It states that number of transistors on a chip doubles every 2 years. So what happens if that is the case? So if the transistors are doubling, automatically the performance and the capabilities of computers will also increase. Then classical computers are approaching physical and thermal limits. Quantum computing offers a new paradigm beyond Moore's law. Quantum mechanics. It is fundamental physics that basically scales the physical properties of nature at atomic and subatomic particles. The key principles are wave-particle duality, superposition, uncertainty, and it is the foundation for our quantum computing. Next topic is quantum tunneling. It will make electrons jump and flow even when the switch is off. That means even when the switch is in off condition, the electrons can easily pass through the circuit or a barrier, whereas classical computer can't. Again, it has the why it will happen, because it has the properties of wave-like behavior particles. And it is the quantum tunneling is important in quantum devices and hardware limitations. Amdahl's law describes the limits of parallel computing speedup. That means in a program, in a parallel processing program, a few instructions have to be performed in a sequence. Will have a limiting factor on program speedup, such that you may think that the complex problem can be solved by adding more processors to make it parallelism and run faster. But that is not the case. Even if you have the infinite processor, sequential parts limit the total speed up. So to solve this, we are going to use quantum computers, which is beyond the parallel limits. Yeah, this is the most important topic in our journey. Quantum properties. Superposition entanglement. Superposition is a mix of 0 state and 1 state. and also entanglement is qubits become linked state of one affects another. These properties enable quantum speedups and secure communication. It's too early to discuss these two topics. I'll discuss in coming classes. Quantum decay. It occurs when a quantum system interacts with the environment, causing the delicate quantum states to collapse into definite classical states. This happens due to laws of superposition. Okay, that means the quantum computer will lose its properties when it exposes to the environment. So this is the major challenge to build a quantum computer that should be stable for our computation process. Okay, yeah, differences between the bit and the qubit. Yes, bit is a binary state, whereas qubit is a quantum state. Bit has binary representation of zeros and ones, and qubit is having a single bit 0 and 1, or we can call it superposition. Qubit allows for quantum parallelism and interference, whereas measured result is classical, but quantum computation happens before that. That means in a quantum circuit, the measurement will be in classical, but the computation that has occurred behind will be completely quantum computation. Okay,